In video number 20 in the Foundations of Computational Economics course, we're talking about Markov chains, or finite Markov chains to be exact. Markov chains are essential for economics. They find applications in all different fields, economic theory, econometrics, definitely computations. In the second part of the course, when we talk about the dynamic models, we will use Markov chains pretty much everywhere as building blocks. So let's take a step back and remind ourselves about stochastic processes. So you can think of stochastic processes of random variables that have a time dimension. So these are objects that describe evolution of random variables in time. Easy example of a random process is a random walk. That's essentially an x of t, a variable that takes discrete values and in discrete time either takes a step up or step down from its previous value with some probabilities which usually do not depend on xt or time. A very well-known stochastic process is a Wiener process or Brownian motion, and this stochastic process is defined as having normally distributed increments, and it's usually set up in a continuous time. That's very important in financial mathematics. Now, a Markov process is the stochastic process which has a Markov property, and that's essentially that the probability distribution over the next period state, or x period x, next period x, only depends on the current period state, xt, and not on the path that the process has taken before that. So Markov property is essentially memorylessness, absence of memory. The distribution of the next values do not depend on the previous values, and they can only depend on the current value of the process. And finite Markov chains are a special case of the Markov processes. Now, the finite Markov chain is a stochastic process which takes values from a finite set S. This set is called state space. Time is discrete. The probability transition from xi in S to xj in S, usually denoted as pi ij, only depends on xi and not on anything that happened previously. So the Markov property is satisfied. And we can write it like this explicitly. The probability of t plus one value of the process, conditional on the whole history of the previous values, is just as well can be conditioned just on the last value because it doesn't depend on anything before. And it's denoted Pij. All right, let's look at the example. Think of this three-state system, and we can talk about weather here. The weather can be sunny, partially cloudy, and rainy. Different errors show the transitions of the process. So with probability 1/2, the sunny day remains to be a sunny day tomorrow. With probability 0.4, it transfers to a partly cloudy day. And from there, with probability 10%, it can be a rainy on the next day or next hour. It doesn't really matter, and so forth. So if it's rainy, then the probability 60%, we are remaining in the rainy state. That's the physical process that can underline or can be represented by a Markov chain. Let's write a Markov chain for this process. So the state space in this case is composed of the sunny, partially cloudy, and rainy states. And let's denote them x1, x2, and x3. And this way we can use the indices for denoting the probabilities. You can verify that these numbers, the probabilities written on the screen here, correspond to the probabilities on the picture. Now, combining all of these probabilities of transition from I to j into a matrix, we get something that is called a transition probability matrix. So just to repeat, every element in this matrix denotes the probability of transitioning from ith to jth state. Right, so 0.5 is to remain in the first state, 0.4 is to go from first to second, and 0.1 is to go from the first to the third. And the same for every other row or an element of this matrix. You could notice that each row of the matrix forms a probability distribution, right? Because these are the probabilities of transferring to the next period states from each of the current period states. And because we're transitioning within the state space S, then each row has to sum up to 1. So each row forms a probability distribution. And this is essentially what defines, or what we call, a stochastic matrix. This is the matrix where all elements are non-negative, and each row sums to 1. And of course, transition probability matrix is stochastic itself. Now, just to repeat, a finite Markov chain is then a sequence of discrete random variables defined on S that have a Markov property, and naturally, the Markov chain is fully characterized by its transition probability matrix, P. So when we work with Markov chains, a lot of the times, to think or to answer questions about the Markov chains, the easiest way to go about it is to just simulate a sequence of realizations. So simulate the Markov chain. To do that, all we need is to know the transition probability matrix, and also, where the initial values come from. And let's assume that they come from some initial distribution psi. So the algorithm is very simple. We draw the initial value x naught from this psi distribution, and then at every step, given the current realization xt, we draw xt plus 1 from the discrete distribution given by the appropriate row of matrix P, of the transition probability matrix. Let's write that in the code. So imagine, we will be using Numpy, of course, since we're working with matrices. Imagine that P is given with this. And psi is an array of 1 by 3, or it's actually one-dimensional array with 3 elements. I want to separate my output with a new line. And here we are. So this transition probability matrix P is actually the one that we already saw on the slide. And the initial distribution is some arbitrary distribution that I've written down. Let's check that it's actually a distribution, right? The numbers sum up to 1. Okay, so in order to simulate a Markov chain, we need to be able to simulate discrete random variables. Let's write a simple function for that. What does this function do? It's a discrete draw. First, let's check that the past, so the only argument is the given probability distribution. So let's check that the argument that is passed is a one-dimensional array, just in case. Then we can say that, or check whether it sums up to 1. So how do we do that? We sum all of the elements of this array, we subtract 1, and we take the absolute value. Of course, I couldn't write it simply as like that, right? The sum of the probabilities equals 1. Why is that? Well, that's because 1 is an integer, and summing up floats, which what transition probability will likely be, may be misleading, as we discussed in an early video on the number representations. So instead, we want to compare the distance, or the distance between the sum of the probabilities and 1 to some low constant, small constant. And so, yeah, probably 10 to the minus 10 is sufficient here. Okay, so how to generate a discrete random variable. It turns out that it's very convenient to calculate the cumulative sum of the probabilities, and this, of course, gives us sort of like a cumulative distribution. To see how it works, let's comment this out and just print CDF here, and I can call the function with some what should be in P-array. Actually, to make it work with lists, let's see. Let's insert one more comment here. So in case props is not an Numpy array, then it will be. So let's give it some distribution. Oh, and it gives an error. Past probabilities do not sum up to 1. Yeah, that's, you know, it's a neat check. It's convenient to have that. So what, it should be 0.5. Okay, now look, this CDF, the summed up distribution, summed up probabilities, the first element is the same, but the second one is the sum between the first and the second, and the third element is the sum of all of them. So if I add more values here, that's what we see, right? This is a cumulative sum of the probabilities. Okay. So what happens then? Then we are drawing one random variable distributed uniformly on 0, 1. And for that, we're using this random uniform command from NumPy. So U is now a drawer between 0 and 1. And a CDF is a vector which takes, which is sort of like the right side of the interval where U could fall, right? It could never go above 1. So this is the right side of the interval. And we can just compare it to it. So the next 3 lines work like this. If I'm going to compare all of this right sides of the intervals in the CDF. Therefore, I cycle through I from first one to the number of elements in CDF. And if U is less or equal, that particular right side of the interval, then we just return I. So let's think how it works. If the generated random U is really small, and so it's below the first value in the CDF, well, then the return will be just 0. And that corresponds for the U to fall in between 0 and this first number, in the first interval, sort of say. Now, if that's not the case, and so U is above 0.1, but below 0.5, then it will return 1. It's going to be it's going to be the second iteration of the loop. I is going to be 1, and that means that U fell into the interval between 0, 1, and 0.5. So it fell into the second interval, and so forth. If U did not fall under 0.5 and didn't return, then if it fell under the 0.7, then we would return 2, corresponding to the generated uniform random number to be between 0.5 and 0.7, and so forth. So we basically return the index of the interval in the CDF where the generated U happens to be. And then because U is generated uniformly, then essentially we're converting the uniform random variable 0, 1 into the discrete random variable by inverting the CDF. All right, so that's this function. Just to check how it works, let's run a little loop. For 10 values, we'll just print the I and the draw from psi. By the way, I should mention that psi can be written in Jupyter Notebook by writing it as LaTeX and then pressing Tab. Oh, I'm still printing something here. Let's not print CDF. And run this again. And you can see in different iterations, that's what happens. We are generating from psi, which we could also print from this distribution. Right, 2 is the most probable, and so we get lots of 2s, more of 2s than anything else. All right, now this function simulates the Markov chain using the algorithm that we just saw on the previous slide. The input arguments are the transition probability matrix, the initial distribution of the chain, and the number of time periods in which we want to simulate this particular chain. As in the previous function, let's convert the p and the psi to the Numpy arrays, just in case they were given as lists. And now I want to check whether the p is the stochastic matrix. So how do we do that? Now we're going to sum p by along the first axis, and that's of course not the 0th axis, that's the first axis, which is horizontal. So we're summing by row. We take 1 out of those sums. The sums are going to be creating a vector. So this is still a vector. The absolute value is a vector, and whether absolute value is less than 10 to the minus 10 is a vector of logical of Boolean variables. And so if all of them are true, that's when we pass this assertion. Otherwise, the P is not a stochastic matrix. Now, in this line, we just check or remember how many values this chain can take by looking at the number of values in psi. And then here in line 10, we are allocating the space to all of the values that will be simulated. And this is for efficiency reasons. Allocation of memory is an expensive operation, at least when we are doing the simulation many times. And to prevent reallocation, we can just set aside this big chunk of memory, namely T slots, and we will be generating integers. So let's just say that this should not be larger than what an integer takes. Okay, the initial value will be drawn from psi distribution, and then we just loop over T, and each time we draw from the discrete distribution, which is given by the row of the transition probability matrix. And by the way, this int, I don't think it's needed. All right, and then we return the whole X, so return the whole simulation. Let's see how it works. Transition probability matrix is given here. The distribution of the initial value is given here. And here's the simulation. It's just created by this line number 3 by calling the function for 100 time periods. And this is what it returns, right? A sequence of 0s, 1s, and 2s. Now, because we were talking about weather, and these are just indices, we can actually convert these back into the weather descriptors by creating a list of the descriptors and then printing the one which was simulated using the I as indexed in CM. So element of SM. The element of SM can be indexed in the array of some values if we want to see sort of more of a physical representation of the process. And of course, the sequence is different every time we rerun this because the draws are obtained independently. So this is the simulation of a Markov chain, pretty straightforward. let's talk about the marginal distributions. So given a Markov chain with the transition probability matrix P, assume that the distribution of xt is known. So at some time t, the chain takes values from the distribution which we can denote psi of t. Now, can we say something about the distribution of the next period value? Or more generally, distribution of the value of the chain after so many steps, after m steps, in fact? Well, we can. And this is how it's done. So let's just write down the probability that xt plus 1 takes a particular value. Right, say y. What's the probability that xt plus 1 takes the value y? Well, that's the probability that there is a transfer to y from x, from this x, multiplied with the probability that xt was x at the previous time period. And this is just a law of total probability. We sum this up over all possible x's that could have been the values of the chain in the previous period. So this can nicely be written in matrix form. So this is the same formula as on the previous slide, but look at this. These are the elements of the matrix P, right? These are exactly Pij. And these are the elements of vector psi t, where I say psi t of I to denote the element of the vector psi. And so the answer that we're looking for is just equal to this expression here. But knowing the rules for the matrix multiplication, we can just write it in the matrix form like this. So if psi t is a row vector, then multiplying it on the left with this transition probability matrix gives us the distribution of the next period value. Pretty neat. All right, this can be repeated for as many steps as we want. For example, m steps. And the only thing that will change is that instead of multiplying with the transition probability matrix, we would be multiplying with the power of the transition probability matrix. And of course, because it's square, there's no problem of taking the powers. And now we have the formula for the distribution of the Markov chain after m steps. That's just the power of the transition probability matrix that we need to compute. Now let's try to do that. So once again, I'm just printing the transition probability matrix and the initial value distribution. And then distribution in one period, this is just going to be matrix multiplication of psi and p. In two periods, we just need to multiply with p again. But then in multiple periods and 10 periods, we need to take the power of the matrix. And you should be aware that the power calculated like this doesn't work. And that's because the power operator is calculated element-wise, not like matrix multiplication. So instead, we need the matrix special command, which is linear matrix power. Okay, we take in p to the 10th power. Let's run this, and what do we see? The distribution of the initial value is this. The distribution of the value in one period is slightly different. In two periods, it's slightly different. And every time this distribution sums up to 1, as you can see. And then in 10 periods, the distribution looks like that. Wonderful. Now, when we take the powers of the transition probability matrix, we can also interpret it as containing the probabilities of reaching a particular state in so many steps. So imagine that p to the power m is just denoted q, and then I can look at the elements of q. Well, it turns out that the probability that xt plus m is j, given that we start at xi, is given exactly by the elements of this Q matrix. And it's easy to see, indeed. Assume that the psi of t is a degenerate distribution, and apply the formula that we just showed. And that will give us the a row of the first row of this matrix Q, and its elements, of course, will correspond to different destination states J. And this can be repeated for the degenerate distributions psi of t, where one sort of moves to every possible location. And that's how you can convince yourself that what's written here is true. All right. That's probably it for the structure of the transition probability matrix. Now, irreducibility and aperiodicity are two central concepts in Markov chain theory, and so let's look at them. Two states I and j are said to communicate if there is positive integers k and l, such that p to the power of k and the element I of j of that matrix. So what this says is that we take p to the power of k and then look at the element ij is greater than 0, and the p to the power l element ij is greater than 0. So in other words, states I and j communicate if there's some number of steps k that you can take to reach j from I, and that's exactly what this this condition is, so that the probability of transitioning there is positive. And conversely, you can get back from j to I in some L steps. If that holds for every pair of states, then the Markov chain is called irreducible. And the way to visualize this is that this is the irreducible Markov chain is the one that has all of their states linked together, and they're linked in both ways, right? It's possible to go somewhere and then come back. Now, aperiodicity is better explained on the counterexample. A periodic Markov chain basically cycles through the states in some predictable way. So, for example, here, if we start from state 1, then we will with certainty go to state 2, and from state 2 we will with certainty go to state 3, and from state 3 we will with certainty go to state 1. Okay, so this matrix implies that the Markov chain will just cycle through states 1, 2, 3, 1 all the time. So more formally, we can say that the stochastic matrix is aperiodic and the Markov chain is aperiodic if the period of every state is 1. Okay, what's the period? Well, the period of a state is the greatest common divisor of the integers where it's possible to go from I to I. There's a typo here. It should be like this. So if it's possible to go from I to I in k steps, okay, then k enters into this collection of integers. So for the last example, these integers are 3, 6, 9. For state 1. State 1 will definitely be taken in period 3, 6, 9, and so forth. And so the period of the state 1 is then 3. Again, the stochastic matrix is aperiodic if the period of every state is 1. Okay, so it's impossible to predict perfectly how the matrix cycles. Now, another notion which is very important for the Markov chain analysis is stationary distribution. Stationary, and also called invariant distribution, is such distribution which I denoted psi with a star, such that if we take one step and look at the distribution that results from the psi star distribution in one step, we get exactly psi star again. Okay, so that's the distribution which does not change if the Markov chain takes one step. And of course, it follows immediately. That means that it doesn't change if the chain takes any number of steps, right? Because we can plug this into this formula and reduce p to the power of k one by one and get just psi star all the time. It's quite obvious. Let's look at that. So let's look at some psi, which I've just written to be 0.4, 0.4, and 2, and repeat the calculation that we did last time. Well, distribution of the initial value is this. Distribution in one time period, and this is where we multiply psi with p, is exactly the same. Distribution in 2 times periods, that's where we multiplied psi with p twice. That's also the same, and of course in 10 times it's also the same. So we have guessed the stationary distribution of our matrix P, transition probability matrix P. That's what it is. Now, does it always exist, a stationary distribution? There's a theorem which is very easy to show from the Brouwer's fixed point theorem that every stochastic map has at least one stationary distribution. Well, it is a typo here as well. That should be matrix. So every stochastic matrix has at least one stationary distribution. All right. Again, that's because the stationary distribution is simply a fixed point of the mapping from row vectors psi to row vectors psi after multiplication with the transition probability matrix. Now, yet it's important to note that a stochastic matrix may have multiple stationary distributions. And for example, the periodic stochastic matrices may have an infinite number of stationary distributions. Uniqueness. This is a very important result in the Markov chain theory. Namely, if stochastic matrix is both aperiodic and irreducible, then it has exactly one stationary distribution. And moreover, for any initial distribution of psi naught, it holds that the psi naught multiplied with the power of p to the tth power of p only deviates from the stationary distribution by an amount that that approaches zero as t approaches infinity. So in other words, if we calculate the distribution of the chain in t periods, then it converges to the stationary distribution as t approaches infinity. That's a really nice property. So given this second clause of the theorem, we can formulate the following algorithm for calculating the stationary distributions. We can start from arbitrary distribution and then just update the psi, the distribution of the state space, by multiplying the previous approximation with p. And, we can stop when the previous iteration approximation and the current iteration approximation are indistinguishable in some sense. And of course, under the uniform ergodicity, and that was the condition essentially of this theorem, So conditions of the theorem, often called uniformly ergodic, or the matrix that the transition probability matrix that satisfies these conditions. So under these conditions, convergence is towards the stationary distribution, of course, and that's because that's the only one which is stationary in that case. Okay, so let's try to implement this in the code. Let's start with the degenerate distribution, where all of the probability mass is at the first point in state space. The transition matrix is going to be the same, and we'll just iterate for 50 times. We will update the psi distribution by multiplying it with the transition probability matrix P, and we will essentially just print it. Okay, and this is what we see. So we start with 0.5. After first, we start with 1, 0, 0. After the first step, multiplying it row by column, we will essentially just pick out the distribution given in the first row of the transition probability matrix, and that's here. But then as we multiply it again and again in step 2, 3, and so forth, you can see that it changes, but then it sort of seems to tend to the 0.4, 0.4, 0.19, and then at some point just switches to 0.4, 0.4, 0.2, where it remains stationary, and we've seen this already. We know that the 0.4, 0.4, and 0.2 is the stationary distribution for our matrix, transition probability matrix P. So here's everything seems to be working. We are converging in about 26 steps. We are converging to the stationary distribution. To conclude talking about the Markov chains, let me notice the notion of ergodicity, which is to say that if we calculate the average time or average number of periods that the Markov chain xt spends at the point of the state space J, then this average time will converge to the element of the stationary distribution psi star as capital T approaches infinity. So here the bold 1, that's the indicator function, which is simply equals to 1 when the condition holds. The convergence is with probability 1 over here, and the result does not depend on the distribution of the initial value. Well, this is an application of the law of large numbers for Markov chains. But it's still a remarkable result that the stationary distribution not only plays a role in the marginal sense, showing the distribution, sort of a cross-sectional distribution of the Markov chain, but also shows the time series dimension or distribution across the time series dimension in the sense of the average time spent in a particular state. Okay, this concludes the lecture on Markov chains, or an introductory lecture. For further learning resources, feel free to check out the CompEcon lecture on the same material. And I'll see you in the next video.